Okay, thank you. Okay, good morning, everybody. My name is Thompson from the University of Bristol, and I'm going to spend the next half hour or so talking to you about an integrated photonics approach to quantum communication devices. This is a collaboration between the University of Bristol, University of Glasgow, and NICT. I'm going to talk particularly about two types of devices. One, related to a quantum communication device so that we can coherently distribute quantum information between separate integrated photonic circuits. And then at the end of the talk, I'll talk about a new approach to looking at chip-based quantum key distribution devices. First of all, before diving into that, I'd just like to motivate to you guys a little bit the area of chip-based quantum information technologies. And so this is a slide that I often put up, which is, I would probably say this is about state-of-the-art in quantum optics experiments. This is an experiment by Jianwei Pan and colleagues done back in 2012, and it's an 8-photon experiment. It produces an 8-photon entangled state. They use it for looking at topological error-corrected protocols. And it's a beast of an experiment. It must have took some poor student, I don't know, maybe a couple of years to put this thing together and get it working. And it's a tour de force. Now, the thought of making an experiment twice as complicated as that, or 10 times as complicated as that, I think is beyond the stretch of any PhD student. And so really, the way I go about motivating looking at integrated photonic technologies is really taking these sorts of ideas, these levels of complexity, and then bringing state-of-the-art photonic engineering approaches and principles, applying them to these sorts of experiments, and then realizing miniature millimeter chip-based devices with all of that complexity on the chip that then allows us to scale up those experiments. And so this is work that we pioneered at the University in Bristol with the first results in 2008. And the reasons to go for this approach are not just because of the miniaturization, which a lot of people latch onto, but it's really about this second point here of stability. By taking your quantum photonic circuits, which are often Mach-Zehnder interferometers or nested Mach-Zehnder interferometers and need to be highly stabilized circuits, by locking those circuits into solid blocks of silicon or solid blocks of glass, you get inherent stability. And then with inherent stability, that then allows you to start increasing the complexity of those circuits without requiring huge amounts of stabilization. And then with increased complexity comes routes towards stabilization. So it's really about the stability that we get from making these circuits in an integrated platform. And so over the last sort of several years, we've used this approach to realize a whole raft of different quantum information experiments. So things like logic gates, 2-qubit logic gates, 1-qubit logic gates in an integrated architecture, proof of principle quantum simulations, so looking at quantum walks of multiple indistinguishable particles, and being able to make more complicated circuits, doing things like proof of principle factoring algorithms, these sorts of things. So a whole range of different experiments that we've done, and there's been a lot of experiments being done by other members of the community within this area. I'd just like to sort of highlight one most recent result of ours, which is this work that we did in collaboration with NTT and was published a couple of months ago now in Science, and we call it the Universal Linear Optical Processor, and it's effectively a completely arbitrarily programmable linear optic processor. So this device effectively has 6-mode input, 6-mode output, and then a raft of nested Mach-Zehnder interferometers where we can individually control the phase on the Mach-Zehnder interferometer, effectively each one acting as a variable beam splitter with a controllable global phase element. And we'd be able to use this device to do any experiment you could possibly ever want to do on a 6-mode in, 6-mode out optical circuit. And so we constructed a 5-photon source, injected those photons into the circuit, reconfigured it thousands and thousands of times to perform a whole raft of different experiments, including heralded logic gates and boson sampling gates and circuits, and a whole raft of other things. And so it's a very, very versatile programmable device. And if you look at what this device looks like, it's pretty large. This is based on a glass based material system. And it's a 10 centimeter size by 4 centimeter size device. You get about 2 of these onto a single wafer. And so we're now at the point again where you can imagine going twice as complex with this technology, but not 10 or 100 times more complex. And so over the last couple of years, we've been looking at ways of moving towards a more miniaturized technology, so we can go beyond the limits of this glass-based approach. Ways of bringing additional functionality. How do we get photon sources onto these devices? How do we get photon detectors? How do we get all the fast control electronics integrated? And then really moving towards a fully integrated quantum technology platform. And so we've looked at a range of different material systems that are available in the sort of quantum photonics, in the photonics community. At the moment, we've pretty much sort of settled on looking at the silicon-based material system. It's a CMOS compatible material system. It uses exactly the same fabrication techniques that are used to make microprocessors that sit inside your laptops and your iPhones. And what this allows us to do is confine light to these incredibly small dimensions. To give you an idea of how small these waveguides are, here's a human hair, and there's the waveguide relative to the human hair. And so we're now taking 1.5 micron light, and we're confining it down to waveguides that are just a couple of 100 nanometers in size. This allows us to get very high confinement, very small bend radii, and we get a million-fold improvement in the component density compared to those glass waveguide circuits that I showed you before. So a lot of headroom for now expanding the complexity of these circuits. So over the last couple of years, we've been doing just that. We've demonstrated photon sources in this silicon architecture. We've demonstrated multiple sources on a chip, showing that those sources can be identical to each other and can produce indistinguishable photons. We've scaled that up to do qubit entanglement on a chip and manipulation of that qubit entanglement on a chip. It's one of our most recent devices where we've now got 4 sources on a chip producing an arbitrarily controllable entangled state that we can then put through an on-chip entangling gate. This gives us complete control. We can entangle and disentangle. We can do phase estimation algorithms. And so we've been scaling this up. Now the question is how much can you scale this up? So we can look, before that, this always makes me a little bit nervous, this plot. This is my quantum photonics Moore's law plot. Okay, so this is actual experimental data of these devices. We've only got 4 points, but it's exponential, right? So, I mean, if we look at this, 2016, we should be at 100. Just so happens that a device has just come out of our lab, what we're looking at now, which has 100 components on it. So we're tracking this trend, right? How high can we go? If we look at the classical photonics community to see where they're at, these are the sorts of circuits people are now realizing in the classical photonics community. People are getting of order 10,000 individual components operating coherently on a single device. So there is a lot of headroom for us to maneuver within. So it's promising from that aspect. But as we continue scaling these things up, at some point we're going to hit the size of a wafer as we're getting towards our, I don't know how many components. And you're then going to start thinking, well, we now need to start getting quantum information off chip. We need to start moving quantum information between chips. And that might be because your wafers are too small or the yield is too low and you need to start making multiple wafers and stacking them together and moving information on and off chip. It might be because you actually want a centralized entanglement system and then you want to distribute out that entanglement, whether that's for things like blind quantum computing, remote quantum sensing, distributed quantum computing applications, or tests of non-locality. But there's a compelling argument to be looking towards what might quantum photonic interconnects look like in this type of architecture. And so that's what we've been looking at, and we've created these 2 chips here, which is a quantum photonic interconnect. And what this allows us to do, these are 2 silicon-based devices. On the first device, we've got these 2 photon sources that work coherently together to produce a qubit entangled state on chip. So we pump with our laser beam, we split the laser beam that weakly pumps both sources. We generate an qubit entangled state with 1 qubit represented as the upper and lower paths here, and the other qubit represented as the upper and lower paths in this arm. And these 2 qubits are entangled with one another. What we then do, we take one of those qubits and we put it through what we call a Path-Polarization Converter. I'll say a little bit more about that in a minute. But effectively, it takes our path-encoded qubits, converts them to polarization-encoded qubits, so we can then couple into an optical fiber, transmit it over a distance, and then couple it back into another path-to-polarization converter back into path encoding. And so we've been now able to coherently distribute a path-encoded qubit on this chip to a path-encoded qubit on this chip. Then what we do is we use these state tomography circuits here and here to allow us to then project and measure the two halves of these entangled states to show that we actually have been able to coherently distribute entanglement across this chip. Just a few more details. The photons are produced using a spontaneous four-wave mixing approach. This is what one of the sources looks like. It's effectively a very long, sort of 2 centimeter long waveguide that we've spiraled up to make it nice and small. We're convinced that it's producing quantum states. The way we convince ourselves by that is we look at these fringes here. This fringe is the classical interference fringe in a Mach-Zehnder interferometer, so just a bright light interference fringe. This double fringe is the result of effectively the noon state being generated by these sources implemented in a Mach-Zehnder interferometer. So we can see that we get very high quantum interference visibilities of, in this case, 99.3%. So really high quality photon source. This is the path-to-polarization converter. It's effectively a two-dimensional Bragg grating. And what it does is light coming in at this angle on this waveguide gets converted into TE polarized light. Light coming in this angle gets converted into TM polarized light. And so we can then take our two orthogonal path states and convert them to two orthogonal polarization states. And so we were able to analyze how well that worked, and we see these are the polarization states that we've injected in to analyze this, and these are the corresponding path states. And we can see that there's some small deviation, but on the whole, we get about 98% fidelity between path to polarization conversion. And this is the full experiment, where the chip on the left-hand side is generating two entangled photons. We then take one of those entangled photons, we do a path to polarization conversion, distribute it to the other chip. We then do tomography on both of those separate qubits on two separate chips, and we're able to show that we see the kind of classic entanglement-like fringes, and we get a violation of the entanglement of the Bell type violation of around, in this case, around 77% violation. So we've been able to coherently create and distribute entanglement across these chips. We can also look at other types of encoding. So polarization is one particular way, but it's limited to a two-dimensional space. If you want to, say, try and now transmit qubits across systems, you want to move to looking at different degrees of freedom. And orbital angular momentum is one particular degree of freedom that lends itself to having high dimensional space. And so this is a device that we published back in 2012, which is a path to orbital angular momentum converter. It's effectively a ring resonator with little nanoteeth on the inside. And these nanoteeth effectively scatter light out of the resonator and put a twist on the light as it comes out of the resonator. And that imparts an orbital angular momentum onto the light. Just to prove that that's the case, here are the phase diagrams of the light coming out of the device. And we can see we can tune it so that we go from effectively 0 orbital angular momentum to these +4, -4. And you can quite clearly see the spirals that you get from the orbital angular momentum. And so we can put multiple devices together on the same waveguides. It's a very compact device. I've got a little video, if this works, just to show you what these look like. So this is a single emitter, and this is 3 emitters next to each other. And this is where I hypnotize the audience. It's quite mesmerizing. But so these are very compact devices that produce these sort of orbital angular momentum states that you can see coming out. And so the long-term vision here is that we can have these devices coupled to these chips, now allowing us to transmit not just two-dimensional qubit information, but QDIT information between multiple devices. Okay, so I call that sort of chip-to-chip quantum communication, because you're actually clearly moving entangled states between chips, and entangled is about as quantum as you can get, so it's a really good measure for how good the quantum communication between these chips are. The next experiment I'd like to talk about is a chip-based approach to quantum key distribution, so specifically focusing on QKD-like applications. And so I think the motivation's pretty clear why you want to go to a chip-based approach. These are the sort of current state-of-the-art semi-commercial and commercial systems that you can get in QKD. And if you take the lid off one of these boxes, there's a whole bunch of optics inside those boxes. It might be bulk optics, it might be fiber-based optics. And the strategy here is can we use the same approaches, the same photonic engineering integrated circuit principles to allow us to crunch all of the optics down to millimeter-sized chips. And the reasons for that, to do that, are because, well, it's compact, it's low cost, it's energy efficient, lends itself to mass manufacturing techniques. And in the long term, these sorts of photonic circuits are compatible with microelectronic processing techniques. So in the long term, you could imagine having all of your electronics and all of your photonics completely integrated onto the same circuit. And eventually, we could imagine maybe QKD devices embedded inside microprocessors. So this sort of approach lends itself to that sort of future thinking. So this is the experiment that we've demonstrated, which is the first demonstration of a chip-to-chip quantum communication system. So what we have here on the upper side, we have the transmitter chip, which is an indium phosphide-based transmitter chip, contains all of the photonics on that chip for the transmitter. And at the bottom here, we have the decoder chip, the Bob chip, which is made from a silicon oxynitride material platform. I'll just go into these in a little bit more detail. The transmitter chip contains 17 discrete individual photonic components. These include on it the laser, so it has on the chip the laser to produce the weak coherent state. We then have pulse modulators, phase modulators, intensity modulators, the diodes for detecting and stabilizing the system. This is all compact into a 2 by 6 millimeter size device. So just to give you an idea, that's my little finger, not my thumb, and that's the device just there. So very, very, very compact device. And with this device, we produce time-bin encoded quantum states. The technology platform that we use is an indium phosphide technology platform. It's a very sophisticated technology platform. It's mainly used in high-end telecommunication devices. And effectively, what we can do is we can actively and passively grow multiple quantum wells within this material system. So we can have all of the active devices like detectors and modulators and amplifiers, and we can have all of the passive devices like filters and low-loss waveguides. So we can realize in this one technology platform a huge array of sort of very useful components. And in a way, it's sort of likened to the kind of transistor, resistor, capacitor that you have in electronics. From that, you can make whatever you want. And here we've got optical amplifiers, phase modulators, polarization converters, waveguides, and that's the toolkit that we can use to make a whole array of different types of photonic circuits. This is what the tunable laser looks like that we have on the chip. The tunable laser is effectively a semiconductor optical amplifier surrounded by 2 distributed Bragg reflectors. And that works as a single wavelength source. We get single wavelengths with line widths of around 34 picometers. We get very good side mode suppression ratios of very, very pure single mode line width, so 50 dB extinction ratios. And we can tune it. We can temperature tune it. We can put a reverse bias across those Bragg reflectors to change the refractive index and tune it using the Bragg reflectors. And so with this device, we can get a 10 nanometer tuning, which in the future will lend itself towards moving towards high bandwidth WDM type wavelength division applications. It has a very low threshold as well, so all in all, it's a very nicely performing on-chip laser. The phase modulators use, they're electro-optic phase modulators. They use something called the quantum confined Stark effect to get very fast phase modulation. We can modulate these devices up to around the 10 gigahertz, which is plenty fast for the sort of things that we want to do. And what we do is we run the laser CW. We then put the laser through one of these phase modulators in a Mach-Zehnder configuration so that we can effectively switch the signal on and off. We can do that very fast, and so we're able to produce these very clean 130 picosecond wide pulses with really high extinction ratios. So we're about sort of 30 dB extinction ratio here. So really, really clean optical pulses that we can then use for our time bin encoding. So this is what we do. This is an example of a BB84 protocol. these are the 4 states that you need for your BB84 protocol. Your 0 and 1 states are realized by the 2 positions of your time bins, so the left or the right position. And then your plus and minus states are realized by a superposition state of your time bins with a relative 0 or pi phase shift between them. And then these are some of the metrics. So we've got about 600 picosecond difference between the 2 pulses and extinction ratio of around 30 odd dB. The receiver chip is it's made from a different material system than the laser. So for the receiver, you want it to be as low loss as possible. And so we use a glass-based material system called silicon oxynitride. And then on that device, we've got 23 individual photonic elements. And these include an asymmetric Mach-Zehnder interferometer to do the time bin decoding. We've got a tunable delay line so that we can tune the repetition rate of our system. We've got balancing Mach-Zehders, we've got tap-off Mach-Zehders, and the whole device, just like the transmitter, is a completely reconfigurable device. Just to give you a little bit more detail what the tunable delay line looks like, effectively we have 3 Mach-Zehnder interferometers with 1, 2, and 4 long delays on that. And by reconfiguring those Mach-Zehnder interferometers, we can switch in and out different delay lines, and that allows us to have 8 separate time bins. So you can see the 8 separate time bins here. The longer the delay, the more the loss, because obviously the more waveguide it has to go through on chip. And we can program this to dial up any delay that we want between 0 and 2 nanoseconds with 300 picosecond steps. We also clearly require quantum random numbers to run the QKD protocol. And so to get quantum random numbers, what we do is we reconfigure our Alice chip with the laser into this sort of configuration, the very standard source plus beam splitter plus detectors. And we use the Alice chip to generate the quantum random numbers. We then use a Bernoulli factoring algorithm to give us a balanced coin, and we use those random numbers then to control the basis states, the bit states, the decoy intensities, the phase randomization for all of the different QKD protocols. And in future generations, we'll integrate both of those together on the same chip. So this is an example of the BB84 protocol. These are the 4 different basis states that I mentioned before. And this is what we see in the receiver. And so you can see that you get your 0 and 1 states are discriminated by the different positions, and your plus and minus states are discriminated by the interference at this peak in the center. And if we look at how that performs in terms of a QKD protocol, we're running this with 150 picosecond pulse durations and 600 picosecond difference between those pulses. And we're getting really reasonable performances from this, sort of comparable to what you might expect from the majority of the high-end systems out there. In this case, we're simulating the length of the system by inducing a loss within there, rather than propagating it through fiber. But we don't believe that the dispersion within the fiber will cause too much of a problem for this system. And we're getting clock rates. We're operating at around 500 megahertz clock rates. We're getting 1.6 megabit per second key generation rates with quantum bit error rates of around 1.4% for a 20 kilometer simulated link here. So these are actual experimental numbers where we simulate the distance through adding attenuation into the system. We've also, because of the reconfigurability of the device, not looked at just the BB84 protocol, but we can run pretty much any protocol we want on this device. And so we've reconfigured it to allow us to look at the coherent one-way protocol, the differential phase shift key protocol. Again, getting really good performance from each of these different protocols. So we're operating devices up to clock rates of around 1.7 gigahertz. We're getting bit error rates as low as 1.4%. We're getting key generation rates of up to 2.35 megabits per second. So all in all, very high-end performance from these devices. Future directions with this, where we want to package them up into deployable prototypes. And then our plan is then to deploy them within the Bristol citywide metropolitan network that we're establishing as part of the UK Quantum Communications Hub. So we hope to have some live demonstrators on the go within the next year or so. And the long-term sort of applications of these, I think, because of the very compact nature of these devices, the energy efficiency of these devices, it potentially opens up for applications that people haven't really previously thought about for QKD. So we're now at the point where feasibly these things, potentially could be inside mobile devices, potentially could be integrated very close or with inside microprocessors, and looking at the more short-range quantum communication applications and what potential opportunities there might be for QKD within these devices. And so with that, I'd like to draw to a conclusion, showing you two quite different types of quantum communication chip-based systems. One silicon-based for coherently communicating quantum information between devices, which might lend itself to sort of quantum computing technologies. And another approach where we're looking very specifically at quantum key distribution using indium phosphide-based and glass-based materials to get high-performance chip-based quantum communication systems. So with that, I'd like to thank you for your attention.
Thank you very much for the fascinating talk. Questions, please.
Yeah, please.
Yeah, please.
Yeah, thank you. This path-to-polarization converter looks really nice. However, if the main purpose is to transmit a two-path encoded qubit from one device to another, wouldn't time binning be a lot easier?
Not necessarily, and the main reason being is because on one chip you then have to go from path to time bin encoding, which requires delay lines. Delay lines on chip are horrendously lossy. And then on the other side you then have to go from time to path, which will require some kind of active element and some active demultiplexing and potentially time bin delays as well. So it's really not, we've thought about it, but it's really not that feasible.
Okay, further questions? Yes, please.
Hi, I wonder how you stabilize your chip, or you don't need to.
The stabilizer, I mean, because it's, as I said right at the very beginning of the talk, because we're now writing these things inside a block of glass, effectively, you get massive stability gains from that. And effectively with these chips, we do relatively little stabilization. So with the receiver chip that has the delay line on it, effectively we set the temperature of this, and we can control the temperature really quite well. And once we've set the temperature, the whole thing remains completely stable. We then use this phase shifter to then calibrate and just tune the system to get the minimum quantum bit error rate. And then once we set it, it remains, as long as we've got decent temperature stabilization, which for these sorts of circuits is no problem whatsoever, the whole thing remains completely stable. And you contrast that to a fiber system or a bulk system where you're having to stabilize the temperature over a much bigger range. We're stabilizing the temperature now over literally just a couple of centimeters.
Okay, thanks.
Please, Marco.
In this figure, you can see the detectors are out of the chip, right?
Absolutely, yes.
So my question is, what are the coupling losses in this case? And also I'd like to ask if a non-reciprocal device like an optical isolator can be integrated.
Right, okay. So yeah, so the detectors are off chip. I mean, the long-term strategy is to look at getting detectors on chip, but we're a good way from doing that. The coupling losses are because of the fact that we're using a glass-based material system. One of the reasons we went for it is because of the low coupling losses. So I think in this case, we're getting about 2 dB coupling losses, which is actually quite high for a glass-based material. So feasibly, we should in future devices be able to get that down below a dB or even half a dB. So really efficient off-chip coupling. And like I said, in the long term, we'd like to move to looking at whether on-chip-based detectors are possible. There's some work in silicon germanium detectors in silicon that might eventually lead to avalanche photodiodes in the silicon, fully integrated into silicon, which is very exciting. And then your second question was about on-chip isolators. It is possible. There are proof of principle demonstrators of on-chip isolators. The problem is you need to have effectively a material that has a magnetic susceptibility that allows you to sort of have this kind of non-linear bidirectional interaction with the light, which is a very difficult thing to realize. So people have realized them, but they're lossy and they're not very practical and they're not readily available. So we have absolutely no plans to put isolators into these systems.
Okay. Last question, please. Yeah, so two questions, but quick ones. Yeah, okay, please.
Hey, it's a nice talk. I just want to comment on the multi-photon entanglement or the linear optics quantum computing. I mean, from my point of view, the most difficult part is the probabilistic nature of the PDC photon pairs, or the brightness of photon pairs, and this kind of thing, the source quality, actually. So is there any method for the integrated optics, photonics, you can fix the problem? On how many photons you are aiming, or how many photon entanglement you have achieved? Yeah.
Right, yeah, so we're still in the relatively low numbers in terms of what we've achieved because it's early days. We believe that we'll be able to target the 8 photon and beyond within probably, I don't know, the next maybe two years maybe. We can probably sort of rival the current state of the art in bulk. In terms of going beyond the sort of 12 photon level, we hit this probabilistic barrier that you've just mentioned because the photons pair sources are all probabilistic. To get around that, we do have ways to get around that. It's something called photon source multiplexing. What it requires is to integrate active and fast feed-forward switching into these systems. But it's well understood. It's an idea that's been around since about 2001. We know how to do it, and that's what we're basically working towards, effectively an actively multiplexed, deterministic on-chip photon source. And once you have that, then scaling up becomes not a problem in terms of the probabilistic nature of the sources.
Okay. Last question was from that side. Yeah, please.
I'm sorry. Maybe a little bit technical. So you said that you're going to use a silicon APD for detector, right?
No.
No?
No, we use superconducting because it's all at 1550 nanometers. So
okay, what would be the timing jitter for that?
It's on the detectors.
Yeah.
I think we're about 60 picoseconds.
Okay.
Okay. This was. There are really a lot of questions to the speaker. I suggest this can be continued afterwards. We have to move on because we are anyway after schedule. So thank you very much again.
Thank you.